Yeah, thank you, Chairman. I'm Shinji Watanabe from Kyushu Institute of Technology. First of all, I would like to thank organizers for giving me opportunity to talk about our recent activities. Today, I'll talk about Grüneisen parameter in quantum critical quasicrystal and periodic crystal, mainly focusing on ytterbium-based quasicrystal. Collaborators are Professor Miyake at Osaka University and experimental members in collaboration with Spring 8 long-term proposal. I would like to thank Professor Sato's group at Nagoya for showing me the experimental data with discussions. The quantum critical phenomena in itinerant electron systems have attracted great interest in condensed matter physics. By changing control parameter of the system, continuous transition to the ordered phase can be suppressed to 0 Kelvin, at which the quantum critical point is realized. The pressure is one of the most important control parameter, which can change the electronic states to tune the system to the quantum critical point. The magnetic quantum criticality, which appears near the magnetic quantum critical point, has been well understood from the spin fluctuation theory developed by Moria and renormalization group theory by Hertz and Millis. However, unconventional quantum criticality has been discovered in heavy electron metal Yb rhodium to silicon 2 in 2000, and similar criticality has been observed in beta Yb4. In both systems, uniform magnetic susceptibility shows power law divergence, giving rise to a large Wilson ratio. To explain the unconventional quantum criticality, we constructed the theory of critical ytterbium valence fluctuation, which accounts for the measured criticality. The common behavior of the unconventional quantum criticality has been observed in several periodic crystals, and the direct evidence of quantum valence criticality has been observed recently in iron-doped alpha Yb4, which is a sister compound of the beta Yb4. And the evidence of critical point of the first order valence transition has also been observed in paramagnetic metal phase of Yb nickel 3 gallium 9 in the temperature, pressure, and magnetic field phase diagram. As temperature decreases, magnetic susceptibility shows diverging increase toward the critical endpoint of the first order valence transition. And surprisingly, the common unconventional quantum criticality has been discovered in heavy electron quasicrystal Yb gold aluminum at ambient pressure. Uniform susceptibility diverges with T2 minus 0.5 dependence, and specific heat quotient shows logarithmic-like increase, giving rise to a large Wilson ratio. The NMR T1T inverse shows the similar temperature dependence to the susceptibility, and approximately T-linear resistivity appears. The quasicrystal consists of the Yb gold aluminum cluster, which has concentric shell structures of first, second, third, fourth, and fifth shells. In the third shell, there are 12 ytterbium atoms. In the first, second, and fourth shells, aluminum gold mixed sites exist. Namely, at these green sites, aluminum or gold atom is located with existence ratio shown here. And there also exists approximant crystal, which has the periodic arrangement of the body-centered cubic structure. So this unit cell has the Yb gold aluminum cluster, which contains these concentric shell structures. And quite interestingly, quantum criticality in the quasicrystal persists even under pressure at least up to 1.6 gigapascal. The magnetic susceptibility shows T2 minus 0.5 divergence from ambient pressure up to at least up to 1.6 gigapascal. On the other hand, in the approximant crystal, magnetic susceptibility diverges with the same criticality as the quasi-crystal around 2 gigapascal, which is sensitive to the pressure. And a new type of scaling called so-called T/B scaling has been observed in the quasi-crystal, where the magnetic susceptibility is expressed as a single scaling function of the ratio of temperature and magnetic field. The T/B scaling with exponent 0.5 is essentially the same as that observed in the periodic crystal beta YbB4. And even in the approximant crystal, the same scaling has been observed as the pressure 1.96 gigapascal. So these results suggest that quantum criticality in the quasi-crystal and periodic crystals is caused by the common origin. Recently, Grüneisen parameter in the quasi-crystal and approximant crystal has been observed. Surprisingly, the absolute value decreases as temperature decreases and finally converges into a finite value. So this value is smaller than the lowest temperature value in the approximant crystal, which shows the Fermi liquid behavior. The conventional understanding is Grüneisen parameter diverges at any quantum critical point. So this result poses a serious challenge to the theory Eva proposed. To clarify the mechanism of these phenomena, we first have to understand the volume effect of ordinary magnetic quantum critical phenomena. After that, we need to analyze the quasi-crystal. So let me trace back to the understanding of magneto-volume effect. As I mentioned, magnetic quantum critical phenomena has been well understood from the SCR theory for spin fluctuations and linearization group theory. Magneto-volume effect was discussed from the viewpoint of spin fluctuations by Moriya and Usami in 1980. However, Kambe pointed out that thermal expansion coefficient in the Moriya-Usami theory does not coincide with that derived from the entropy obtained by integrating specific heat by temperature in the original SCR theory. And he also pointed out a possibility that Grüneisen parameter diverges as the quantum critical point. Then Zhu et al. Evaluated criticality of thermal expansion coefficient and Grüneisen parameter and has shown that Grüneisen parameter actually diverges. So this is the definition of the Grüneisen parameter. By substituting thermal expansion coefficient, specific heat, and isothermal compressibility into this equation, Grüneisen parameter can be expressed like this. Like this. If the system is dominated by a single characteristic scale, Grüneisen parameter is expressed as the volume derivative of the characteristic temperature, and Fermi liquid is known as the typical case. When characteristic temperature depends on the volume, and it becomes zero, Grüneisen parameter diverges. However, it is known that characteristic temperature of spin fluctuation is not zero, even at just quantum critical point. On the other hand, magnetic correlation length diverges at the quantum critical point. So with these considerations, it has not been clarified how Grüneisen parameter behaves at the quantum critical point within the SCR theory. Recently, we have succeeded in constructing the theoretical framework by considering zero point and thermal spin fluctuations under stationary condition in the SCR theory, complete expressions of thermal expansion coefficient and Grüneisen parameter are derived. The specific heat is derived in the form of Ca minus Cb, where Ca becomes dominant at low temperatures. The thermal expansion coefficient is derived as a form of corresponding alpha A plus alpha B, where alpha B becomes dominant at low temperatures. We have found that pressure derivative of the solution of SCR equation Y proportional to the inverse susceptibility exists in the critical term, which was not reported in previous studies. Grüneisen parameter is derived in the form of gamma A plus gamma B, where gamma A is expressed as the volume derivative of characteristic temperature of spin fluctuation, and gamma B is shown to diverge at the quantum critical point. A remarkable result is temperature-dependent coefficient exists in the critical term, which affects the intermediate temperature regime and also affects criticality itself in the case of two-dimensional antiferromagnetic quantum critical point. Namely, in the three-dimensional ferromagnetism and antiferromagnetism, and two-dimensional ferromagnetism at sufficiently low temperatures where these temperature-dependent coefficients are regarded as constants, criticality of our results reproduces the renormalization group theory. However, in the case of two-dimensional antiferromagnetism, these temperature-dependent coefficients affects criticality itself, which was not reported in the previous studies. Then we construct the theoretical framework of critical volume effect for the quantum critical point of the valence transition. To discuss the Grüneisen parameter in the quasicrystal, we construct the periodic Anderson model on approximant crystal because essentially the same critical behavior appears as the pressure-tuned approximant crystal. We calculate irreducible susceptibility and apply the mode-mode coupling theory to the most dominant charge transfer fluctuation. Then we determine the coefficients of the valence SCR equation and solve it. By using the solution, we calculate susceptibility, T/B scaling, and also specific heat thermal expansion coefficient and Grüneisen parameter on the basis of this framework in a unified way. The periodic Anderson model on the approximant crystal is constructed like this. We consider the system with periodic arrangement of body-centered cubic structure of the Yb gold aluminum cluster. Because the existence ratio of the first shell is very small, here we consider the shell structures from second shell to the fifth shell. As a first step of analysis, here we consider the case that aluminum gold mix sites framed in red are occupied all aluminum. The transfer for conduction orbitals between the nearest neighbor aluminum sites is said to be T2, and FC hybridization between the nearest neighbor ytterbium and aluminum sites between third and second shells is said to be V0. And the other transfers and FC hybridizations are set so as to follow this distance dependence with azimuthal quantum numbers, following the LCAO argument and Harrison's rule. The band structure calculated by Slave-boson mean field theory for U infinity for a typical parameter set of heavy electrons at half filling is shown here. Because of strong Coulomb repulsion between Hall F holes, the normalized F level is raised up to the vicinity of the film level, giving rise to the heavy quasi-particle band. We see where F hole level is located at a rather deep position from the film level. So this state is considered to the pressurized approximant crystal. The dominant contribution to the density of states at the film level comes from 4f electron at ytterbium site, and next leading contribution comes from 3p electron at aluminum site on the fourth shell. So this is due to the strongest FC hybridization reflecting the shortest ytterbium aluminum distance. Actually, by calculating the irreducible susceptibility chi FFCC, we found that charge transfer fluctuation between 4f electron at ytterbium on the third shell and 3p electron at aluminum on the fourth shell is considerably enhanced like this. A remarkable result is almost flat momentum dependence appears near gamma point, which is ascribed to the strong local correlation effect for F electrons. To clarify how this local charge transfer fluctuation affects quantum criticality, let us focus on this charge transfer mode because it is overwhelmingly dominant. Then we apply recently developed the model-model coupling theory of critical valence fluctuation and the magnetic field to the present system. Namely, starting from the periodic Anderson model with interorbital Coulomb repulsion and Zeeman term, we derived the valence SCR equation. By solving the valence SCR equation as the quantum critical point, we found that T over H scaling appears over at least 4 decades. So this dashed line indicates the least square fit of the data for large T over H region, which gives the exponent 0.5. And by this relation, the solution of the valence SCR equation turns out to have the T2 0.5 dependence. So magnetic susceptibility as well as the valence susceptibility shows T2 minus 0.5 criticality. So this result indicates that magnetic susceptibility in the pressurized approximant crystal exhibits T2 minus 0.5 for zero field limit, and also T over B scaling behavior as observed in the quasicrystal. Now, characteristic temperature of critical valence fluctuation is 10 to minus 4 in the unit of T2, which is located around the lowest temperature. The emergence of the T over B scaling behavior is ascribed to the small characteristic temperature of critical valence fluctuation. Next, let us discuss the specific heat in the quasicrystal by using these parameters corresponding to the pressure-tuned valence quantum critical point in the approximant crystal. The specific heat near the valence quantum critical point is derived from the entropy of critical valence fluctuation as the form of Ca minus Cb, whose explicit forms are given here. And temperature-dependent coefficient is shown to be calculated by this equation explicitly. The result at the valence quantum critical point in the pressure-tuned approximant crystal is shown here. As temperature decreases, specific heat coefficient shows divergence toward zero temperature. As temperature decreases, Ca term, this part becomes dominant, which shows the logarithmic behavior as observed in the quasicrystal by Deguchi et al. On the other hand, if we try to fit our data for low temperature data with the power law form, we obtained T2 minus 0.66, which can be also compared with the Watanuki's plot in the quasicrystal. The thermal expansion coefficient near the valence quantum critical point is derived in the form of alpha A plus alpha B. In the quasicrystal, the theoretical analysis of the Anderson model, taking into account aluminum gold mix sites, has shown that valence quantum critical points are condensed in the ground state phase diagram, which explains robust criticality under pressure. If we focus on valence quantum critical point, the pressure derivative of the solution of the valence SCR equation is expected to be zero because of many condensation of valence quantum critical points in the ground state phase diagram. Actually, as an experimental fact, temperature dependence of the inverse susceptibility lies on almost the same straight line from the origin, at least up to 1.6 gigapascal from ambient pressure. So this indicates that pressure derivative of this quantity at low temperature is zero, making this quantity zero. So in the quasicrystal, thermal expansion coefficient is expressed as only alpha A term. The result for the pressure-tuned valence quantum critical point in the approximant crystal is shown here. Alpha over T shows divergence toward zero temperature, T2 minus 0.6 dependence. Then, by substituting thermal expansion coefficient and specific heat, and by using the isothermal compressibility at room temperature, we obtain the Grüneisen parameter, whose absolute value decreases as temperature decreases. Because Grüneisen parameter can be expressed like this explicitly, and this part is constant, then it turns out that this decrease reflects the decrease in the ratio of the specific heat. If alpha B term exists in the thermal expansion coefficient, divergence of Grüneisen parameter occurs. So not diverging Grüneisen parameter is a consequence of robustness of quantum criticality under pressure in the quasicrystal. To analyze the Grüneisen parameter in the quasicrystal in more detail, we derived the relation between the characteristic temperature of critical valence fluctuation and Kondo temperature on the basis of periodic Anderson model on the approximant crystal. Here, A tilde and R bar are dimensionless constants which are coefficients of charge transfer mode, and energy difference between conduction band as a Fermi wave number and renormalize F level to the conduction bandwidth. Then the pressure derivative of T0 is given by this equation, which includes the pressure derivative of Kondo temperature. Then Grüneisen parameter is expressed in the quasicrystal is expressed like this. On the other hand, approximant crystal shows ferroliquid behavior at ambient pressure, which is characterized by the Kondo temperature. The Grüneisen parameter is expressed as the volume derivative of Tk, which is expressed like this. Because this factor is in the order of 10 in the typical heavy electron systems, Grüneisen parameter is enhanced by this factor, which is consistent with the measured absolute value 130. And by comparing quasicrystal and approximant crystal, it turns out that difference in the Grüneisen parameters at lowest temperature reflects the difference in pressure derivative of characteristic energy scales T0 and Tk. In the pressure-tuned approximant crystal around 1.96 gigapascal, quantum criticality is observed, which suggests the valence quantum critical point. Because temperature dependence of inverse susceptibility changes under pressure, this quantity is not zero, giving rise to the non-zero alpha B term. Then gamma B term is not zero. So absolute values of thermal expansion coefficient and Grüneisen parameter at 1.96 gigapascal in approximant crystal are expected to be much larger than those observed in the quasicrystal at ambient pressure. This is our theoretical prediction to be measured in near future. Let me summarize my talk. We constructed the complete expressions, specific heat, thermal expansion coefficient, and Grüneisen parameter in the framework of SCR theory for spin fluctuations. Then we have constructed theoretical framework for calculating these quantities near the valence quantum critical point. Starting from periodic Anderson model on the approximant crystal at pressure-tuned valence quantum critical point, I have discussed magnetic susceptibility, T over V scaling, and these quantities in the quasicrystal in a unified way. Not diverging Grüneisen parameter is shown to reflect the robust criticality under pressure, and difference in Grüneisen parameters of quasicrystal and approximant crystal at ambient pressure reflects the difference in the pressure derivative of characteristic energy scales T0 and Tk. So thank you for your attention.